So this is the Spearman rank test. This is a test that is non-parametric and is used for skewed data and finding correlations. The equation is in figure 1, which says 1 minus 6 times the sum of d2, which is 100, over n, which is 8, times n times 2 minus 1. The equation is in figure 1 and figure 2 shows the table of data. First we have to rank each score into ascending order. The second and fourth columns show chest throw and peak flow for 8 participants. We rank both the columns into their individual ascending ranks. We then find the difference between each of the ranks. The sum of the difference between each rank should always be 0. Finally, you must calculate the difference between each score and square that value. Then you find the sum of all of the squared values. You then substitute each value into the equation in figure 1, which comes out at 1.19. So 6 times 100 over 8 times 63 equals 1.19. Then you must take away 1 from 1.19, which equals 0.19. The final step is seeing whether there is a significant difference or not. This is where we use the critical values table. A table of critical values has different levels of significance, such as 0.25, 0.5, and 0.05, etc. And then a column in each of those shows the values for degrees of freedom. Degrees of freedom is a number of values in the final calculation of a statistic that are free to vary. The degrees of freedom for this dataset is n minus 2, so it would be 8 minus 2, which equals 6. Then it's like coordinates. The level of significance is 0.05, and the degrees of freedom is 6, so my critical value is 0.89. For this, if the critical value is bigger than my calculated value, then there is no statistical significance. And in this case, there is no statistical significance because 0.89, which is the critical value, is bigger than my calculated value. So if we go back to the idea of the levels of significance, such as 0.05, which is the standard level of significance for us, it's saying that you are 95% sure that you are correct. If it was 0.01%, it's saying that you'd have to be 99% sure that you are correct. Okay, so if we go on to Pearson's rank. Pearson's is a parametric test. This is a test that is used if the data is normally distributed and is used to find correlation. The original equation is in figure 1, which says n times the sum of x times y minus the sum of x times the sum of y divided by the square root of n times the sum of x squared minus the sum of x squared times by the square root of n times the sum of y squared minus the sum of y squared. Figure 2 shows the data table, and figure 3 shows the substituted equation. The final R value that was calculated was 0.36, and the degrees of freedom was 6. This meant that my critical value was 0.7067. In this case, there was no statistical significance because the calculated value was smaller than the critical value. So every critical values table that you are given, there is always a different idea for whether or not it is statistically significant based on if it's larger than a certain value. Now we're on to the t-test. The independent t-test is a test for two datasets that are the same but come from different groups. In Figure 2 we can see that there is standing vertical jump for Group A and Group B. Figure 1 shows the equation for working out the t-value, which is mean 1 minus mean 2 divided by the square root of standard deviation 1 squared over n1 plus the standard deviation 2 squared over n2. At the bottom left of the table in Figure 2 you can see that it says 14 plus 14 minus 2 equals 26. This is because the degrees of freedom is n1 plus n2 equals minus 2. Because there are two groups, you have the number of values that are in each group and take away 2. Figure 3 shows the substituted values that you have put into the original equation. The process of this test is finding the mean and the standard deviation of both datasets. Then, at the end, once you have found your calculated value, which in this case is 1.278, you do the same as the Pearson and the Spearman rank, where there is a critical values table and you find your critical value using your degrees of freedom and level of significance, which is 0.05. In this case, the critical value is 2.056, which means we accept the null hypothesis as there is no statistical significance. The calculated value is lower than the critical value. This is why there is no statistical significance. Now the dependent t-test. Figure 1 shows the equation for the dependent t-test. This is where there are two datasets that come from the same group but are pre-test and post-test. Figure 2 shows the results table that is collected from standing vertical jump, and Figure 3 shows how the data was substituted into the equation from Figure 1. Figure 1 shows the sum of D divided by the square root of n times the d squared minus the sum of d squared divided by n minus 1. The calculated t-value for this test was 5.08. Once again, the level of significance was 0.05 and the df was n minus 1, which was 5 in this case. This meant that the critical value for this test was 2.015, and because 5.08 is larger than 2.015, there was a significant difference between the two datasets. For all of these tests that I've used in this PowerPoint, as well as the graphs from earlier in the presentation, they have come from an Excel document that shows different results for GB gymnasts. This makes it easier to calculate values such as the mean, median, standard deviation, range, etc. We use software such as Excel, and many universities use SPSS, which is a software package that makes calculations a lot simpler, but is expensive. That's why we use Excel at college. These types of software carry out all of the calculations for you so that you don't need to do it manually. I have found that when I've done the worksheets offline, it has been difficult to calculate values such as standard deviation, as it is very time consuming and there is a lot of room for error, as there is a high possibility of error. Finally, a decision tree. A decision tree is used to determine what type of test should be used for looking at the correlation or difference. On the slide you can see that there is a decision tree. This tree starts with the data. It then goes to ask if you're looking for a difference, correlation, or category. The categories is easy. This is because it is using parametric data all of the time, and the test that you must use should be the chi-squared test. This test is used to test the relationship between two categorical variables. Then there is a correlation. You see if it is parametric or non-parametric. If it is parametric, then you use the Pearson test, and if it's non-parametric, you use the Spearman rank test. Finally, if it is difference that you're looking for, you see if there are two or more factors or just one. If there are two or more, then you use a two-way ANOVA, as we can see here. And if there is only one, then you go to see if there are different subjects or not. If the subjects are both the same, such as here, then you see if it's parametric or non-parametric, following these two boxes here. Then all you use is the test that it recommends, and this is the same on the other side. Just follow each branch that is correct for your dataset and use the test that it recommends at the end. Figure 2 is a simplified way of showing how to determine what test to use. The Mann-Whitney-U test, which is found here, is a test that is simply used to compare differences between two independent groups. Finally, the Wilcoxon matched pairs test is used to compare two related samples.